Welcome. Today, we are going to delve into the fundamentals of cryptography, with a special focus on how it is used within operating systems. We'll explore the essential concepts that underpin secure communication and data protection in the digital world. Let us begin this journey into cryptography basics, encryption fundamentals in operating systems. So, what exactly is cryptography? Cryptography is the practice and study of techniques for secure communication in the presence of adversaries. It is the art and science of protecting information by transforming it into an unreadable format, called ciphertext, ensuring that only authorized parties can access it. Key aspects of cryptography include protecting data confidentiality, ensuring data integrity, providing authentication, and enabling non-repudiation. Let's understand the difference between encryption and decryption. Encryption is the process of converting plaintext, like the message "Hello World," into ciphertext, which appears as jumbled or unreadable data, for example, AX7#P at 3!ZQ. This transformation is done using an encryption algorithm and a key. Decryption, on the other hand, is the reverse process. It converts ciphertext back into its original plaintext form, using a decryption algorithm and the appropriate key. Think of encryption as locking a message in a secure box, and decryption as unlocking it with the correct key. Cryptography can be broadly classified into two main types: symmetric encryption and asymmetric encryption. Symmetric encryption uses the same key for both encryption and decryption. It is fast and efficient, but requires a secure method for key exchange between parties. Examples of symmetric encryption algorithms include Advanced Encryption Standard, Data Encryption Standard, Blowfish, and Twofish. Asymmetric encryption, also known as public key cryptography, uses a pair of keys, a public key for encryption and a private key for decryption. The public key can be freely distributed, while the private key must be kept secret. Asymmetric encryption solves the key distribution problem, but is generally slower than symmetric encryption. Examples of asymmetric encryption algorithms include Rivest, Shamir and Adelman, elliptic curve cryptography, and Diffie-Hellman key exchange. Let's dive deeper into symmetric encryption. Symmetric encryption relies on a single shared key for both encrypting and decrypting data. This shared key must be securely exchanged between the sender, Alice, and the receiver, Bob, before communication can occur. Symmetric encryption is known for its speed and efficiency, making it suitable for encrypting large volumes of data. Common algorithms used in symmetric encryption include AES with 128, 192, or 256-bit keys, data encryption standard with a 56-bit key, which is a legacy algorithm and considered insecure, triple data encryption standard with a 168-bit effective key length, and Blowfish with variable key length up to 448 bits. In summary, Alice uses the shared key to encrypt the plaintext, converting it into ciphertext. Bob then uses the same shared key to decrypt the ciphertext, recovering the original plaintext. Now let's explore asymmetric encryption. Asymmetric encryption uses a pair of mathematically related keys, a public key and a private key. The public key, represented by a lock icon, can be freely distributed and is used for encryption. The private key, represented by an unlock icon, must be kept secret and is used for decryption. Alice obtains Bob's public key and uses it to encrypt the plaintext. Bob then uses his private key to decrypt the ciphertext, recovering the original plaintext. Asymmetric encryption solves the key distribution problem, as the public key can be shared without compromising the security of the private key. Common algorithms used in asymmetric encryption include Rivest, Shamir, and Adelman, based on factoring large prime numbers, elliptic curve cryptography, digital signature algorithm, and Diffie-Hellman key exchange. Let's move on to hash functions. Hash functions are one-way mathematical functions that convert data of arbitrary size to a fixed size output, known as a hash value or digest. These functions have several key characteristics. They produce a fixed output length regardless of the input size. They are deterministic, meaning the same input always yields the same output. They are computationally efficient to calculate, and they are practically impossible to reverse. Common hash algorithms include Message Digest 5, which is 128-bit, which is a legacy and insecure algorithm, Secure Hash Algorithm 1, which is 160-bit, which is deprecated, Secure Hash Algorithm 256, which is 256-bit and widely used, and Secure Hash Algorithm 3, which has a variable length and is the newest standard. The input data hello world, which has a variable length, passes through a hash function such as Secure Hash Algorithm 256, resulting in a hash value such as a 591A6D4040011733CF B7B190D62C65, and so on, which has a fixed length. Now let's discuss digital signatures. Digital signatures are mathematical schemes used for verifying the authenticity and integrity of digital messages or documents. They provide authentication, ensuring who sent the message, ensure non-repudiation, meaning the sender cannot deny sending the message, verify integrity, confirming the message has not been altered in transit, and use asymmetric cryptography. Common use cases for digital signatures include software distribution and updates, secure email using secure or multipurpose internet mail extensions or pretty good privacy, financial transactions, secure sockets layer or transport layer security certificates, and mobile app authentication. In summary, the sender uses their private key to sign a document, creating a digital signature. The receiver can then use the sender's public key to verify the signature and ensure the document's authenticity and integrity. Let's explore the role of cryptography in operating systems. Cryptography is integral to modern operating systems, providing essential security features. Some of these features include file system encryption, such as BitLocker in Windows, File Vault in macOS, Linux Unified Key Setup in Linux, Enterprise Cryptographic File System, and Zettabyte File System encryption. Secure Boot verifies digital signatures of boot components, prevents unauthorized boot code execution, uses Trusted Platform Module, and protects against rootkits and bootkits. User authentication includes password hashing using BCRYPT or Argon2, multi-factor authentication, biometric verification, smart card authentication, and single sign-on systems. Kernel security includes kernel module signing, address space layout randomization, secure memory allocation, system call filtering, and mandatory access controls. Finally, let's consider the current challenges and future trends in cryptography. Some of the current challenges include quantum computing threats to current algorithms, key management complexity, performance overhead in resource-constrained devices, balancing security with usability, and regulatory compliance across jurisdictions. Future trends include post-quantum cryptography, homomorphic encryption, which allows computation on encrypted data, zero-knowledge proofs, blockchain-based security solutions, and hardware-accelerated encryption. Thank you. Questions? If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.